Hi everybody, this is going to be the last video in the molar conversion set. All right, this last one I wanted to do because there are a couple different spins on mole conversion problems that can be a little more complicated than the two steps or the one steps that we saw. All right, so an example of this is number 7. What is the mass of phosphorus in 23.4 grams of Mg3PO4 or magnesium phosphate? All right, so one thing we have to think about when we're asked about an element within a compound is what are the subscripts in that formula telling us? All right, so if we have a molecule of Mg3PO4 and we took that singular molecule and split it into all of the different atoms, we would find that we would have 3 atoms of magnesium, we would have 2 atoms of phosphorus, and we would have 8 atoms of oxygen. All right, now those are ratios where we have 1 of these and then 3 magnesiums, 2 phosphorus, and 8 oxygens. And those ratios have units of moles. So we call this a mole ratio. All right, and we can use that ratio, that equality, just like any other conversion factor. All right, so we've been given grams of a compound, but asked about the mass of an element within it. All right, so we're going to start by taking the grams of that compound and converting that into moles of the compound. And once we're in moles of the compound, then we can use this idea of mole ratios to convert from the compound to the element. And then we can determine the mass of that element within. All right, so for example, we start with what we've been given. We have 24.3 grams of that magnesium phosphate, which is a big, long formula. All right, we need the molar mass of this substance. All right, so we go to the periodic table. We take 3 magnesiums plus 2 phosphorus plus 8 oxygens, add them all up, and we find that 1 mole of this magnesium phosphate substance has a mass of 262.87 grams. I'm just going to use MP to represent magnesium phosphate. All right, so there go the grams of that magnesium phosphate, and now we have moles. All right, but that's not good enough. We need to go from the compound to the element, and this is where our mole ratio step's going to come in. All right, if we look at that compound, for every 1 mole of that entire unit, it contains 2 moles worth of those phosphorus atoms. And that, again, is coming from those subscripts in the formula. That's going to let us cancel those moles of the magnesium phosphate and leave this last step of going from moles of phosphorus to grams of phosphorus. And again, this is going to be a molar mass step. So 1 mole of phosphorus, if we go check the periodic table, has a molar mass of 30.97 grams. All right, so those moles of phosphorus are going to cancel. We're going to be left with grams of phosphorus, which is what the problem asks for. All right, so we go and we check with our calculator, 24.3 times 2 times 30.97. And then we're going to divide that by 262.87. All right, and we find that 24.3 grams of magnesium phosphate contains 5.73 grams of phosphorus. All right, so this looks a little bit different than what we saw above. All right, this step, number 1, which is a grams and mole step, that's familiar. There's our molar mass step. All right, and this step at the end, step number 3, also should be familiar because that's a moles to grams, so that's another molar mass step. It's this step in the middle, number 2. All right, this is your mole ratio step. And again, we're using our subscripts to make that jump from the compound to the element within it. All right, and you can go from the element to the compound in the exact same way. We would just flip that conversion factor upside down. All right, now this mole ratio step is going to be one of your best friends when we get to stoichiometry. It's going to be a little bit different because we'll be moving between compounds in a reaction, but the idea is going to be similar. All right, so let's go look down at number 8. We have a sample of CuNO32, and that contains 2.57 times 10 to the 22nd atoms of oxygen. What is the mass of the sample? All right, so this time we have atoms of an element within a compound, and we're asked to find the mass of that compound. All right, so it's going to be similar to what we did in number 7 because we're talking about an element versus the compound. The difference here is we're going to start with the element. All right, so we start with our 2.57 times 10 to the 22nd atoms of oxygen. All right, and we need to convert to moles of oxygen from atoms. So we're going from particles to moles, so that's Avogadro's number. So 1 mole of oxygen atoms contains 6.02 times 10 to the 23rd atoms. All right, and again, we're putting Avogadro's number on the bottom of this conversion factor so that we can cancel it. All right, now we can't go from moles of oxygen to grams of oxygen because that's not what the question's asking. The question's asking about the compound. So this is where our mole ratio step's going to come in. So if I look at my formula, CuNO3, 2, all right, for every 1 molecule, I have 1 copper, I have 2 nitrogens, and I have 6 oxygens, all right? That 2 gets distributed inside of the parentheses, so 3 times 2 is 6. All right, so I come over to my mole ratio, and for every 1 mole of the copper nitrate, I'm just going to put CN here, all right, we have 6 moles of oxygen atoms. All right, so that's going to let us cancel that mole of oxygen. All right, our last step, we want to go from moles of the copper nitrate to grams. All right, so we're going to use the molar mass. The mole of copper nitrate is going to go on the bottom, and then we need to add everything up. So we have 1 copper, 2 nitrogens, and 6 oxygens. We check the periodic table, add everything together, and we get 187.57 grams for that copper nitrate. So we're going to be able to cancel the moles of copper nitrate, and we're going to be left with units of grams of copper nitrate. All right, so we go back to our calculator, and we type in 2.57 times 10 to the 22nd. All right, we're going to multiply that by 187.57. All right, then we're going to divide by Avogadro's number, 6.02 times 10 to the 23rd, and then we need to divide again by 6. And we get 1.33 grams of the copper nitrate would contain 2.57 times 10 to the 22nd atoms of oxygen. All right, so similar to what we saw in problem 7 above, we've got 3 steps here. All right, step number 1, atoms to moles or particles in moles. So this was Avogadro's number. All right, for step number 2, this was our mole ratio step. All right, where we went from an element to the compound. And then for step number 3, we had moles and grams. So this required the molar mass. All right. So problem number 8 was a little bit of everything. All right, so that should really give you a good overview of the different ways that we can utilize these conversion factors when we move around with the mole. Okay? If you have any questions, please let me know.